In this section of our chapter 22, we're going to talk about aldol condensations, and we're going to look at those reactions with ketones and with aldehydes. So if we look down below, there's an observed reaction down here. So what we have here is an aldehyde or a ketone and another aldehyde or a ketone. So our combinations are ketone and ketone, ketone and aldehyde, or an aldehyde and an aldehyde. Now, this central position here where the carbonyl is one of the spots that we're going to be looking for to identify what type of reaction occurs here. So we look at our carbonyl, and then to the left of that and to the right are the alpha positions, and those positions can react. So depending on how many positions we have there or how many H's we have there, you can get something called a crossed aldol condensation. So in this example, let's just consider that we have on these R positions here, let's just consider that there's no H's just for the sake of making this example a little easier. So this reaction can occur under acidic or under basic conditions. And what happens is we get a new bond that's formed here. And the way that we number this new bond is we take a look at our carbonyl, okay? And then we look over one position, that's your alpha position, and then over one more, that's your beta position. So the new bond has been made between an alpha and a beta carbon, and that beta position has a hydroxy group on it. So sometimes these are called beta hydroxy ketones. Now, the yields of these can often be pretty low. So if you look down here below, it says ketones will react and result in about 20% yield. That's pretty low. In fact, with acetone is your ketone, I think the yields are about 1%. Aldehydes result in about 75% there. Now, the other thing that can happen here is that if we continue this reaction under acidic or basic conditions, and often heat is going to be used here. It's not necessary all of the time. We'll see there's a couple conditions where heat's not required, but often heat is used as an indicator to continue this reaction. You get a dehydration. And then what you get is an alpha beta, unsaturated, because you now have a double bond there. It's a ketone or aldehyde depending on what you started off with. There's a clever way that's used in the lab to shift the equilibrium of that, the formation of that beta hydroxy ketone. So remember before we talked about acetone. Right? Acetone gives you about 1% of the product if you just carry this reaction out all in the same vessel with hydroxide is your catalyst. So instead what you do is you start off down here with just acetone, and then you have this special adapter here that's filled and contains barium hydroxide as the catalyst. So it's in a stationary kind of position up here, so it's immobile, it doesn't move. And then you have a heat source, so the acetone starts to distill, essentially. You start boiling it, right? It boils up here, and of course some of it touches here, but it has a little sidearm where it comes around, and then you have this inlet where you have a jacketed condenser that's running cool water through this. So the acetone condenses, and then it drips back down, and it's bathed through this barium hydroxide. Now, of course, it's it's all kind of warm, but as it drips through that, it reacts and it forms the diacetone alcohol, right? The beta hydroxy ketone. So it drips through there, and then that product drips all the way back down and comes back down into your original flask down here at the bottom. So then you have acetone plus the diacetone alcohol. And the diacetone alcohol does not distill as easily, so it stays put down here. And more acetone comes up and it bathes through this hydroxide solution, right? Your stationary phase up there. And then the product comes back down and hangs out down here. And since there's no hydroxide down here, the reverse reaction doesn't really occur. So you just continue doing this kind of condensation reaction until you have almost 100% of your product there. It's a clever way to drive the equilibrium to the products. So there's interesting biological examples of this too. So So there's an enzyme called fructose 1,6 biphosphate aldolase. So that's what this enzyme is right here. And what it operates on, it's sometimes just called aldolase, but what its target substrate is fructose 1,6 biphosphate. So glucose under metabolism goes to glucose 6-phosphate, then fructose 6-phosphate, then fructose 1,6 biphosphate. And then aldolase sees this and takes it and cleaves it into dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. And so the reverse reaction of this is gluconeogenesis, making of new sugar. So if we look at the reaction here, here is your cyclic form of fructose 1,6 biphosphate. And what's going to happen here is that's going to open up. We'll talk about how that occurs in chapter 23. And it goes into the catalytic site of aldolase. And aldolase has all these proteins as functional groups that react with this molecule. But the first thing that happens here is that you end up having a nitrogen lone pair attacking that carbon, and then this oxygen grabbing an H right here. All right, so here's that bond. That new bond is right here. And then you have that protonated O up here at the top. A base comes in, grabs this H, and it makes a double bond right here. So a protonated Schiff base is another name for an iminium ion. Right? So it's like an imine that's been protonated, right? And then what happens is that another basic amino acid comes over and grabs one of those H's. We come over and we form a double bond right here. And that double bond is this guy. Okay, that's your carbon-oxygen double bond there. And then this bond comes over to form a double bond here, and then you gain a lone pair on your nitrogen down here below. So this part right here is cleaved off, and that's your glyceraldehyde 3-phosphate. Right? Down here you have this enamine, right? Here's an ene, an amine, there's an enamine. It's an intermediate. We have isomerization, right? So we come over here and we again form another iminium ion, or a protonated Schiff base. And then we have a hydrolysis occurring when we have water coming in here, and we kick off your dihydroxyacetone phosphate, and then we have our aldolase back. So there's two parts to this reaction. The first part is the formation of the aldol product, that's the beta hydroxy ketone. And the second part is the dehydration. So let's take a look at those two parts. And in each of those parts, these reactions can take place, remember, under acidic conditions or under basic conditions. So the first case that we're going to look at here is base-catalyzed mechanism of that beta hydroxy ketone formation. So what we're going to do is we're going to take hydroxide. It's going to come over and grab an H here, and then those electrons are going to come over to that carbon. And that's going to form your enolate, right? So this over here is your enolate. And of course that enolate has resonance. So we can come over and we can do this to get the other resonance structure there. All right, now coming from this second enolate resonance structure, these electrons are going to come down here, and then we're going to swing around here, and we're going to grab that carbonyl. So that's going to be our new carbon-carbon bond here. Right? So what that's going to give us is, of course, our oxygen, the negative charge, and that will be protonated with a solvent. Right? So in this case, since we're using hydroxide, probably H2O. And then we get our final product here. So the other thing to point out is that carbon right there, if we're stopping this reaction here, it's technically a chiral carbon. So really, we get two products here. Get your phenyl group there. So you get your OH out, the CH3 here, plus your OH back. So you get a mixture of enantiomers there, technically. Okay, so be cautious of that. Now, if the product is dehydrated, then that's not a concern anymore. All right, so that's your base-catalyzed mechanism. So let's look at the acid-catalyzed mechanism down here below. So we're going to go from our keto form all the way over here to the enol form. So the first step of this is just keto-enol tautomerism. So we're going to come around, we're going to grab that H. Right, that H is from H3O+. So one of our lone pairs will come over and do that. That's going to give us this. Okay, and then this is a compound that has resonance. So we're going to take electrons, plop them up here, and that gives us our plus charge on that carbon. All right, now water is going to come over, and it's going to grab a hold of this H and do that. And that's going to give us our enol. So remember, the keto form usually predominates at equilibrium, but because the enol continues to react, we pull the equilibrium constantly to the right side. Right, now what we're going to do here is see a flow of electrons just like this. We're going to come around and do that, and then this is going to come around and grab a hold of that carbon, and notice that that carbon has already been, the carbonyl of that carbon has already been protonated. Right, so we need to do that because we can't have a negative charge in the presence of a proton solution, essentially acidic solution. All right, so then that's going to take these electrons and pull them up here after we do that. So that's your lone pair up on that oxygen. All right, we have a plus charge right here. Right, that's this OH that's up here at the top. And then this has resonance also, right? So we can take these electrons and pull them right up there. And that would give us this with our positive charge there. All right, so then at that point in time, we're pretty much done. We just have a one last little step to do. So we have water. And in this case, water is going to come around and it's going to grab a hold of that H atom. So we can come over here and we can do this. We're going to grab a hold of that H, and then we're going to swing those electrons down just like so. You could also come over and pull this H off too. So that gives you this product, and then if we just redraw to kind of clean it up, we get that. And of course, that also is that same chiral center, right? So if we're stopping here, that actually would be the same products as we saw up above. So you get your carbonyl, your phenyl group, right? The same two products. And there we have it. Okay, so that's your first step. That's your part one. So then the second part of this reaction is just your dehydration. So of course here this occurs under acidic or under basic conditions. So let's take a look at our basic conditions here. So first step of this reaction is we're going to do a deprotonation. Now notice here that often heat is used. So it's not technically required for every one of these dehydrations, but it's usually included as an indicator to the student as to what you should do. Should you stop at the aldol or do you do the dehydrated product? So in this case, this reaction actually does not require heat. We'll talk about why in just a moment. So what we're going to do is we're going to come over here and we're going to grab one of those H's. We're going to kick those electrons right up to that carbon. So it gives you a carbon here with a minus charge. And then also let's just make a note here, plus resonance. So there's resonance there that I'm not going to draw out with you. So then the next step of this reaction is we're going to take these, come over, swing them down just like so, and then plop off that hydroxy group there is hydroxide. So OH minus leaves. So hydroxide here leaves. It's not normally a good leaving group in an E2 type of a reaction, but this step of this mechanism is actually pretty exothermic. So in that case, it actually can leave. So hydroxide will leave here. So we're going to get a couple of products. So you think about some of your cis-trans EZ type stereochemistry across that double bond. You can have a phenyl group up or the phenyl group pointing down. Now, in reality, pH is not just a small thing, it's a benzene. So it's a big group, right? So which one is it better? Is it better to have a phenyl group there opposite to this or right next to it? Well, it turns out that it's better to have them opposite. So in this situation, that's going to be your major. All right, so some textbooks won't even include this guy. So it just depends on what textbook you're using. And then under acidic conditions, the same general type of reaction is going to take place here. Notice also that we're going to be using heat. We're using H plus here, but really it's H3O plus, right? So H plus comma H2O, sometimes written that way too. So what we're going to do is we're going to take a lone pair and we're going to grab that H. So that's going to do this. It makes that OH into a good leaving group, and we've seen that kind of theme happen over and over again. So what happens next is we kick off water and we form this carbocation. Of course, there's lots of resonance there, and then water is going to come around, grab an H, and we'll get a double bond here. Right, so just as we talked about before, we're probably going to end up getting this as our major product, where those phenyl groups are kind of pointing away from each other and not close to the oxygen up there at the top. Right, so in this case, heat is not required for this specific reaction because you get a high level of conjugation here. So benzene is conjugated with the carbonyl, which is conjugated with this double bond and also conjugated with the phenyl group. So in this case, because you have such a highly conjugated system, you don't really need to heat this thing up.